per gram and 10 amps per gram. And if you're doing testing in the laboratory, and you have, for example, a boss or an advisor, a supervisor who wants you to get through your tests quickly, right? Which one of these would you pick if they were all the same, right? You would pick the one that only takes 500 seconds or 100 seconds instead of the one that takes 3,500 seconds, because you know you can get more tests done if you go to the shorter durations. The other factor in this one is you look for the IR drop. This IR drop in this case is really hard to see because it's so low. So this particular device has very low internal resistance, making it really favorable for high rate devices, so high powered devices. And you might say, well, what about that shoulder? What about this shoulder that I see in the discharge curve? That doesn't look normal, right? Where does that come from? Should that worry you? What would cause some sort of a change in the smoothness of the voltage decay as I discharge the device? If you go back to the last curve, at that point, I'm rolling over one of these pseudocapacitive pumps. That's what's happening. That's what's happening there. Okay? It's kind of hard to translate it perfectly because one of them is constant current and the other one is constant voltage sweep rate. But that's really what's happening. On the right side, panel D, we see a couple of things. Capacitance retention as a function of cycle number. We only went to a couple thousand cycles. Later on we did more. In this case we were kind of comparing to batteries. Battery testing, you'd usually do a few thousand cycles to demonstrate that you have a reasonably good cyclic stability. Okay, and in this case, this is not bad, right? It looks like we've dropped about I don't know, 8 or 10% of capacitance in 2,000 cycles. Coulombic efficiency has to do with whether all of your charge is actually coming back when you charge and discharge, and in that case, the things that can cause bad Coulombic efficiency are things like side reaction. So your Coulombic efficiency is sort of a measure of whether you're having irreversible degradation of your material. So back to our Ragone plot. Here we have energy density on the vertical axis, power density on the horizontal axis. This is a volumetric basis. Okay. And if you look at this performance relative to thin film lithium-ion batteries, this is not your typical lithium-ion batteries, and other supercapacitors, including and an electrolytic capacitor, you see that in this case the power density is high and comparable to what you get in these other comparative supercapacitors or just capacitors, but the energy density is much higher than those capacitors and comparable to what you would get in this thin film lithium-ion battery. So this is kind of the place where you want to be if you're talking about, thinking that supercapacitors would be replacing batteries. Because what this device could do relative to this thin film lithium-ion battery, what this could do is charge in 1, 2, 3 orders of magnitude faster, so 1,000 times faster than the lithium-ion battery, and still have the same amount of energy per unit volume. Okay, so that's an advantage. Now I have to say, larger scale lithium-ion batteries and what you would typically find in devices and phones and consumer electronics, those are not thin film batteries, those are thicker devices. And their energy density is significantly higher than this. So this is not saying we've beaten lithium-ion technology, period. It just is a comparison for thin film things. But then making a device. So when I imagined talking about device characterization, I wanted to make sure that I mentioned that you can play around in the lab a little bit when you do this. You don't have to always just hook your device up to some kind of instrument and push a button or click the mouse and have the test run. You can build something with your hands, and you can make it, and you can stretch it and twist it and roll it and measure it and actually do useful things with it. So in this case, we took that carbon cloth with graphitic petals with polyaniline. In this case, we used a polymer gel electrolyte with sulfuric acid. We made a two-sided device that's shown here. Put in some other things, made good contact using silver paste, which you wouldn't want to use typically in practice, but in the laboratory that's okay. And once we made it, we saw that we could, again, this is cloth-like. It's a layered structure. It has two sides. But we could bend it, that's shown in the bottom panel. We could wrap it around a glass rod, and we could light an LED. So this LED requires 1.5 volts in order to light, okay? And in our case, what we did is we had 3 of these cells in series in order to make a 2.5 volt device, okay? And what happened in this case is that the student who made the device brought an earlier version of this to myself and Professor Reifenberger, who I mentioned before. And Professor Reifenberger, who again is a physicist, but he is an engineer-minded person, said, I don't believe it's any good. I want you to show me that you can light an LED and that it can stay on for, I think he said 10 minutes, okay? And he said, I'll bet you a nickel, which is not very much, right? A nickel is like worth, what, 1 rupee or something, less, and or a little bit more. And he said, I bet it won't stay on for 10 minutes, but in this case, it stayed on for 30 minutes. So the student was very happy, and he was also 1 nickel richer after that. Okay, changing gears a little bit, just because I want to give you a flavor for other possibilities for materials, although it's not too much of a stretch from what we've been talking about. We started with BuckyPaper. You can buy BuckyPaper. It's a funny sounding name if you don't know what it means. Bucky, the word Bucky comes from the Buckminster fullerenes, the C60 material that won the Nobel Prize 25 years ago or so. And so it's a mat of carbon nanotubes is what it is, okay? And you can buy this. It's not very expensive anymore, not too bad. It's about 50% dense with nanotubes. It does some filtering. It has a reasonable resistivity. It's not great. It's certainly not as good as a metal film, but it's not too bad. An ohm centimeter, for those of you who work in sheet resistance or resistivities. So what we did is we grew the petals on BuckyPaper using the same process I mentioned before, and then we coated them with manganese oxide, okay? And so the purpose here was to use an oxide coating, but not ruthenium oxide. Even though you know it's the best oxide, pseudocapacitive oxide material, it's just too expensive. Manganese is much cheaper, and so you could go with you can go with that and get some pretty good performance out of it. And manganese oxide is still, very. It's still I think a very good material for this. And then we used an aqueous electrolyte as shown here. So here's the CV curve. It looks pretty good, not quite rectangular. The bottom ones are pretty good, are pretty well rectangular. In this case, we're showing you the different stages of growth. So if we just have BuckyPaper with that electrolyte, you get this, double layer capacitance, but it's really small. When we add petals to the BuckyPaper, again in that electrolyte, so that would be like a double layer capacitor. We get the red curve. When we have manganese oxide on BuckyPaper alone, we get the blue curve. And then when we have everything together, BuckyPaper, petals, manganese oxide, we get the top curve. So this is not different scan rates. This is showing the effect of the materials. Okay, and that's nice to see, where you can see that you're really bolstering. So going from red to blue, you're adding pseudocapacitance. Okay, and you see the shoulder a little bit from the pseudocapacitive hump. But you're going from red to blue, you're adding pseudocapacitance, and going from blue to gold, you're adding surface area. Okay? So as we look at this, if you look at the specific capacitance as a function of scan rate, again, you see that when you go to very low scan rates, you end up with the highest capacitance because your CV curve is more rectangular. And then it decays because you have some internal resistance. But in any case, you get to the point where this, you've increased your capacitance by more than tenfold by using these materials. Okay? You also see something, and I think it's important to recognize, when you have comparative tests like this, the CV curve on the left, the CV curves, they're a family of curves, those are each different materials. Okay? And if you and the fact that the shape of the curves is generally similar, they have humps in the same place, they have a general rectangular-like characteristic, that tells you that the measurements were done in a consistent way. It doesn't mean that's how it happened at first, right? In fact, when we started doing these experiments, there were some problems with the equipment, and the curves were not consistent. And so then we did this, and we got to the point where we could repeat it over and over again. And that's when we said, okay, this is good. We'll go ahead and call this, start to reach some conclusions from this. Here's the charge-discharge for the BuckyPaper sample. And you can again see very, very low internal resistance. You have, again, the energy density is going to be listed here. As we go through this, we can use this data in order to calculate our capacitance. When you have your voltage, your maximum voltage, then you take that. Capacitance times maximum voltage squared times 1/2 is going to give you your energy, the energy storage capability for that material. Now, I haven't said anything about the minimum voltage, that's the total. And then we normalize by mass to give us our energy density or specific energy. And then you can take, once you have your energy density and you know how long it took to completely suck all of the energy out of that system, then you can calculate your power density. So on the Ragone plot again, this is more useful perhaps. We are comparing here the petals with polyaniline to the BuckyPaper petals with manganese oxide, and also comparing it to a lot of other things. But I like this graph because we actually we superposed it onto something that gives some other comparison. So this is energy density on the vertical, power density on the horizontal axis, and these diagonal lines going through tell you how long that discharge took. Okay? Because energy and power are related by time. All right? And so in looking at this, so if I have low energy density, then it would take only a short amount of time, right, to fully discharge that device. So it's a useful comparison. And so we look at this and we see the batteries here are in the hour range, right, for time, the duration to fully discharge them. Lead acid battery. Lithium ion is a little bit better than the others, but it has lithium ion has higher energy density than other batteries typically, and higher power density. That's why it's so popular. Okay. But look at the comparison to the PANI-based, that's the polymer-based pseudocapacitive material, and the manganese oxide. And here we're talking about the PANI-based material. If you kind of look at the middle of the purple curve where that line intersects, at that line, you could look at the system here. This number 36, right, is coming from the fact that we're converting hours. We're converting seconds into hours. It comes from 3600. So we had 3.6 seconds, 36 seconds. The next one would be, what would that be? 360 seconds. So that's 6 minutes. That's what that line corresponds to. And then you have an hour. and these are decades in time. And you see that this would be 6 minutes, and in the middle of that purple sweep, and that would give you the energy density of a lithium-ion battery, but you'd be able to charge it in 6 minutes. Right? So technologically, that's important. The MnO2 pseudocapacitive material is a little bit worse in terms of energy density. Still not bad, though. It's comparable to lithium and nickel cadmium, lead acid. But it tends to have a higher power density, so it could go faster. All of these results came from where? There is no Ragone Plot machine out there. It came from CV curves, charge-discharge curves, and the analysis that goes with it, right? So just to wrap this up, I think I'm right on time. Making an impact. So again, I want you to be thinking about always taking what you do to the next level, beyond your laboratory, beyond your testing, and be thinking about what would it take to go to the next level. You see that the materials that we talked about testing today were chosen not because they're the best, because if we wanted to find the best material, instead of manganese oxide, we would have taken ruthenium, right? We know that that's better. Polyaniline is not necessarily the best conducting polymer, but it is